Today we are going to deal with UART serial port programming for STM32 F446 microcontroller.
Generally, there were two types of data transfer, serial data transfer and parallel data transfer. This also we have seen. What is the advantage of parallel data transfer? Simultaneously, you can send multiple bits. Normally, 8 bits will be sent. But what is the disadvantage? These many external lines are required. More hardware connections are required. But in the case of serial data transfer, through a single transmission line and through another single reception line, you can send as well as receive data. The parallel data will be converted to serial data and it will be sent bit by bit from the sender to receiver and back. So what is the advantage of serial data transfer? Number of hardware connections are less. And what is the disadvantage in the serial transmission? Since you are sending bit by bit, it will take little time for all the data that is to be received in the receiver. But in parallel data transfer, simultaneously the whole data can be sent. But generally, nowadays we are using serial transfer in order to reduce the circuit complexity. So these were the three types of serial transfer. One is known as simplex. That means transmitter is transmitting directly to receiver. Another one is half duplex. So in half duplex, how it will work? Both the blocks can act as receiver as well as transmitter, but only one at a time. That means one block will be acting as a transmitter for time t. At that same time t, the second block should be acting as a receiver. So one will be transmitting, other will be receiving. And after some time, first can be acting as a receiver, second can be acting as a transmitter. So both can actually perform reception and transmission, but only one operation at a time is performed. Then full duplex means what? Both the blocks can act as transmitter as well as receiver at the same time. So normally UART is coming under this category. Both the transmitter and receiver or both the systems can act as transmitter as well as receiver at the same time. Transmit and receive data at the same time. So two separate dedicated pins are there. Then this is a framing structure for sending a particular data. If it was A, ASCII value of A will be sent. So what was the frame, how it was done? You will be sending a start bit. So start bit is nothing but 0 because I already told that normally the pin which is used for serial transmission will be pulled up always if data transfer is not there. If data transfer is not there, it will be pulled up. And when the data has to be transmitted, it will take this line to low so that the receiver can understand that some data is going to be received or transmitted from the other end. So that low bit is known as start bit. So whenever this 0th bit is received by the receiver, it identifies that from next bit onwards data is going to come. So this is known as the start bit. Then corresponding 8 data bits will be there. So in this case, first LSB is sent, then MSB is sent. 4-1 means first LSB is 1, that is 0001. MSB is 4, that is 0100. So in this case, LSB is sent first, then MSB is sent. Then in order to show that the transmission of data is over, stop bits are used. So stop bit is nothing but the pin will be taken from low to high. Right. So pin will be taken back from low to high. Right. So you can have either one stop bit or two stop bit according to the configuration of the program. So this is known as frame format for UART data transmission. Right. So here you can see start bit will be going out first, then last will be stop bit. So this is how the data is sent. How will you connect the controller with the say serial transmission device or a PC? because I told that let us take this is PC. In PC it is RS232 format. In the controller it is TTL format. So you will be using an IC known as MAX232. It can perform to and fro conversion from TTL to RS232, RS232 back to TTL. So this is how the pin should be connected. TX of microcontroller should be connected to T1 in of MAX232. T1 out should be connected to pin number 2 of PC. 2 means it is receive of PC. Similarly, RX of microcontroller should be connected to R1 out because microcontroller is reading data. So R1 out should be connected to RX. R1 in should be connected to pin number 3. Pin number 3 is actually the transmit pin of PC. So whatever data is transmitted will be in RS232 format. That should be connected to R1 in of MAX232. So RS232 will be converted to TTL and it is available in R1 out. That R1 out will be given as input to RxD or input to the microcontroller. So the RS232 data is converted to TTL. The TTL data can be read by the microcontroller. But in the transmission case, TX pin of microcontroller will be sending data in TTL format that will be connected to T1 in and that will be converted from TTL to RS232 in T1 out. That T1 out data can be sent to pin number 2 of PC. 2 means it is received. So whatever TTL data is sent from microcontroller, corresponding RS232 data can be received on the PC. So these are the pin numbers present in DBN connector of the PC. DBN connector is used for serial transmission, right? Out of this, you will be using only these 3 pins, 2, 3 and 5. 2 is data receive of PC, 3 is data transmit of PC, 5 is ground. So this connector also we have seen before. So 2, 3 and 5 only will be used. 2 will be receive, 3 will be transmit, 5 will be ground.
So this is a block diagram representation of STM32 446 Nucleo board. So here you can see this is a STM32 F446 microcontroller. It is connected to another block in the board itself. It is known as StLink. So StLink is used for debugging, programming as well as for virtual serial communication between the STM32 and the PC which is connected through the mini USB port. So the microcontroller is connected to an embedded ST-Link. It is a separate embedded system which is attached to the Nucleo microcontroller board part. So through this STM32 ST-Link we are going to interact with the microcontroller and the PC. So interaction are of 3 types. It can be either used for programming the STM microcontroller or for serial communication or for debugging purpose. So this is a block diagram representing that. So this is your host PC. Host PC is connected to the STM32 Nucleo board. So the Nucleo board consists of 2 parts. One is the STM link part and the microcontroller system part. So the PC is connected through the USB to the Nucleo board and it is connected to the ST-Link part of the Nucleo board. So ST-Link is used for debugging the controller through this SWD pin, that is serial wire debug pin. It is used for programming as well as for serial communication through the UART2 pins. So the programming part will be done through the UART2 RX pin, that is PA3. That means whatever program you are writing in the PC will be sent through the ST-Link to the UART2 RX pin, that is PA3 of the microcontroller, so that the transmitted program from the PC can be received by the microcontroller through the UART2 RX pin. Similarly, for the serial transmission, both the UART2 RX and TX pin, that is PA2 and PA3 will be used. So whatever data you are sending from the microcontroller will be sent to the PC through the TX pin via the STLink part, and whatever data you are sending from the PC will be sent through the STLink and will be received in the microcontroller at the UART to RX pin. So the STM part will be used for serial transmission, programming as well as debugging of the microcontroller. So these are the USART features. What is the expansion of USART? Universal Synchronous Asynchronous Receiver Transmitter. So this peripheral can be used for synchronous as well as asynchronous transmission and reception. So in STM32 we are having UART starting from USART1 to USART6. Out of that USART1, 2, 3 and 6, it can perform both the synchronous as well as asynchronous transmission and reception, but UART 4 and 5 can only perform asynchronous transmission, that is transmission as well as reception. That is why here 4 and 5 is known as UART and the others are known as USART. Synchronous and asynchronous is supported, but here only asynchronous is supported. So from this table you can clearly see that the synchronous mode and the smart card mode, these two modes are not supported in UART 4 and 5. But all the other features are common for both USART as well as UART. You can go through this features. So, and this is one of the important thing, both the USART and UART, the data length can be configured as 8-bit or 9-bit. 8-bit means 8-bit data can be transmitted. In 9-bit data transmission, in addition to 8-bit, one parity bit also will be sent. So this is the listing of the registers which are used for configuring the UART. So USART status register, data register, baud rate register, control register 1, control register 2 and control register 3. So these are some of the registers which you need to configure for configuring the UART as well as USART. This is a simplest or simplified block diagram of a USART. So whatever data you want to write, that will be sent through this bus. PW data means parallel write data. So whatever parallel data, that is 8-bit data you need to write, it will be sent through this bus, and that data will be sent to a register known as transmit data register. So whatever data you need to send, you need to write it into transmit data register, right? The parallel data will be sent to transmit data register, and from there the data will be sent to a shift register known as transmit shift register. What is the function of this shift register? It will convert parallel data to serial data that can be sent through the TX pin, because USART is used for serial transmission, but you are sending an 8-bit parallel data that needs to be converted into serial data. That is taken care by using this transmit shift register. So once the data you have written to the transmit data register will be sent immediately to the transmit shift register, and whenever the transmit shift register is getting a clock from the baud rate generator, each bit will be shifted out through the TX pin. Generally the LSB pin will be shifted out, then the next bit will be shifted out, and finally MSB pin will be shifted out. So this is in the case of serial transmission. And how the reception will take place? Since it is serial programming, the received bit will be received on the RX pin bit by bit, and whenever a bit is received here, it will be sent to another shift register known as receive shift register. So what is the speciality of this receive shift register? It is a serial to parallel shift register. That means it will be getting the serial data through the RX pin bit after bit based on the baud rate clock. Whenever it is getting a clock, one bit which is received in RX will be shifted in to the shift register. Similarly, in each clock, bit after bit it will be shifted into the shift register, and finally when 8 bits are received here, or complete byte reception is over, the data will be sent to a register known as receive data register. So once the whole data has been shifted into the shift register, we have converted the serial data into parallel 8-bit data. So that 8-bit data will be sent to RDR or receive data register. From the receive data register, the data will be sent to the bus and we can read the data. What type of data? Parallel data. So this is how the serial transmission and reception is functioning. So both this operation can be performed either under the control of the CPU or under the control of the DMA. If we are using DMA, CPU can be offloaded from controlling this operation or performing this operation. Then before going into the configuration of UART, we need to first of all configure the clock. What type of clock we are using for the system clock generation. So for that we are using a register known as RCC CR register. RCC stands for Reset and Clock Control Register. In that control register, that is reset clock control registers or peripherals, control register we are using for controlling the clock source. This register will be automatically configured or by default this will be configured to a particular value, but here we are only understanding this. So according to my configuration, I need to configure HSI, that is high speed internal clock, as my clock source. That is what I am going to do. By default anyway, HSI will be the clock source for system clock. HSI will be generating 16 MHz clock. That will be the clock source for the system clock. But how this register is configured, that is what we are seeing here. So RC oscillator frequency, that is internal RC oscillator frequency, can vary from one chip to another due to the manufacturing process variations. Because since we are using high speed internal clock, we are depending on the internal RC oscillator for the clock generation. But due to variation in the manufacturing process, there can be some changes in the frequency generated by internal RC, right? So each device is factory calibrated by the STM for 1% accuracy at 25 degrees Celsius. So it is factory calibrated. That calibration value is written in the ST microcontroller itself. And at the time of reset, what will happen? The factory calibration value will be loaded onto HSI calibration bits 0 to 7. That factory calibration value will be loaded onto HSI calibration 0 to 7. So to these bits, 0 to 7 means it is actually bit number 8 to 15 of CR register of RCC. So HSI calibration 0 to 7, that is actually bit number 8 to 15. That value will be loaded with the calibration value from the given by the ST. And if the application is and this calibration value loading to HSI bits will be done automatically at the time of reset. We don't need to do anything. And if the application is subjected to some voltage or temperature variation, this can affect the oscillator speed, right? It can affect the oscillator speed. And the HSI frequency can be trimmed by using HSI trim 0 to 4 bits. So normally calibration value will be loaded, and if you want to trim this calibration value based on the voltage and temperature variation, right? If there is a voltage and temperature variation, we can trim the calibration value or we can adjust the calibration value by using HSI trim 0 to 4 bits. HSI trim 0 to 4 bits, that is 3 to 7 bits of RCC CR. So we can write some value here so that the calibration value can be adjusted based on the voltage and temperature variation. And by default, the HSI trim value and these two bits will be configured. What is that configuration by default? We will see in the next slide. So here we can see that this is the same RCC control register. RCC control register reset value is 000XX83. What do you mean by 83? 3 means the last 2 bits are set. What are the last 2 bits? HSI on bit and HSI ready bit. What is the function of HSI on? HSI means internal high speed clock enable bit. So internal high speed clock is enabled. So the last bit, 0th bit is 1. By default, HSI oscillator or internal high speed oscillator is enabled. Then HSI ready, what is the function of that? It is internal high speed clock ready flag bit. Whenever the high speed clock is stable and it can be used by the CPU or the system clock, it will be set as 1. So by default, once you are performing the reset, HSI on bit will be 1. Then when the clock is stable, HSI oscillator ready bit also will be 1. Within few nanoseconds, it will be made as ready. So both HSI ready and HSI on is 1, 1. Then the trim bit, by default, the trim bit will be 1, 0, 0, 0, 0. That is why by default 83 is there. 8 stands for 1, 0, 0, 0, 0. So by default, I have already told STM has factory burned a calibration value into the controller. When you are resetting the controller, STM32 has already provided a calibration value in the controller. At the time of reset, that calibration value will be automatically loaded into HSI calibration value, these bits. That is why it is shown as XX. We don't know what is that calibration value which is loaded by STM. That is why it is don't care, it is XX, that is undefined. At the time of reset only this value will be loaded, and since there is voltage and temperature variation, we can change this HSI trim value so that calibration value can be trimmed. By default, the HSI trim value is written as 1, 0, 0, 0, 0. If you want to change this, we can change. By default, the reset value of RCC CR is 83. That means HSI is on, HSI ready bit is 1 and trim value is 1, 0, 0, 0. Then this is a block diagram showing to which interface or to which bus interface our UART peripheral is connected to. So I have told that we are having 6 UARTs. So UART1 and UART6, it is connected to APB2 interface, which is high speed advanced peripheral bus, that is APB2, and UART2, UART3, 4 and 5. These 4 UARTs are connected to APB1 interface, that is low speed advanced peripheral bus, that is APB1. So why we need to understand this? Because whenever you are configuring these UARTs, you need to configure the APB1 clock. Right? We have already seen that there are prescalers which is used for configuring APB2 and APB1. So if you are using or configuring any of these UARTs 2, 3, 4 or 5, we need to configure the prescaler for APB1. If you are using UART1 and UART6, you need to configure the prescaler for APB2. That is why we have gone through this block diagram. So now for time being, in our program we are configuring UART2, so it is connected to APB1. So we need to configure APB1 prescaler. So this is a block diagram showing the clock generation for UART. So we have already seen that system clock is used as clock for almost all the peripherals, and HSI is the clock source for system clock. By default HSI is operating on 16 MHz. So 16 MHz is given as input to the UART peripheral, and since the UART2 is used in the program, it is connected to APB1 bus interface. So we need to configure the prescaler for APB1, and since APB is connected to AHB, we need to configure the prescaler for AHB also. So system clock is connected to AHB peripheral or AHB bus. From the AHB bus, APB bus is deriving its clock by dividing the AHB value by any of this prescaler value. Finally, the APB1 clock is connected to UART. So, when you want to configure the baud rate for UART, we need to configure the prescaler of AHB as well as APB. Both the prescalers you need to configure. For AHB, we can have prescalers from 1:1 to 1:512. APB, we can have prescalers from 1:1 to 1:16. So, what do you mean by prescaler basically? Prescaler, what does it do? Let us consider that my prescaler ratio is 1:1. What does it mean? If we are giving one clock at the input of this AHB prescaler, which is configured as 1:1 prescaler ratio, you will get one clock. When you are giving one clock, you will get one clock at the output. If the prescaler ratio is 1:1. If the prescaler ratio is 1:2, what does it mean? If you are giving two clocks at the input of this prescaler, you will get only one clock at the output. Similarly, if the prescaler ratio is 1:4, if you are giving four clocks at the input, then we will get only one clock at the output. That means whatever clock you are going to give as input to the prescaler, by configuring the prescaler, you are actually dividing the clock by these values. So, if the prescaler ratio is 1:4, what does it mean? You are dividing the input clock by 4. That is why when you are giving 4 clocks at the input, you will be getting only 1 clock at the output. So, similarly by configuring APB prescaler, what does it happen? The output of AHB will be again divided by this value. So, whatever clock you are generating as output from the AHB, that will be again divided by any of this. So, if the APB prescaler is 1:2, what does it mean? The AHB clock will be divided by 2. So, when you are giving 2 AHB clock at the input of APB, then only you will be getting 1 clock at the output. So, by configuring the prescaler, we are actually configuring the frequency of the clock or the time period that is given to the UART. So, this clock will be used for generating the baud rate for UART. Baud rate means what? It is nothing but number of bits transmitted or received per second. I have already told that whenever the UART is getting one clock, one bit can be received or one bit can be transmitted. So, at what speed the number of bits should be sent out or received, that is known as the baud rate. Number of bits transmitted or received in a second. That is dependent upon the clock which you have configured here. That is known as a baud rate clock. It is done by a block known as baud rate generator. We will see how to configure that in the coming slides. This is a register known as RCC CFGR, that is Reset and Clock Control Peripherals Configuration Register. So, RCC Clock Configuration Register. This register is used for configuring the APB2 prescaler, APB1 prescaler as well as AHB prescaler. In my case, I am configuring UART2. So, actually I need to configure the AHB prescaler, that is configured by bit number 4 to 7, and APB1 prescaler which is configured by 10 to 12. Right? APB2 prescaler we don't need, but what are the reset values we will see here. So, RCC configuration register, the reset value. What do you mean by reset value? When you are resetting the controller, what is the value stored in this CFGR? So, here the reset value is 00. So, what does it mean? Bit number 13 to 15, it is used for configuring what? It is known as PPRE2, that is APB high speed prescaler. Right? So, these PPRE2 bits are used for configuring the prescaler for high speed advanced peripheral bus 2, that is APB2. So, by default, these 3 bits are zeros. Here all the bits are 0, that means bit number 13, 14, 15 are zeros. What do you mean by that? 0, 0, 0 means APB prescaler is not there. So these three bits are 0, 0, 0. What does it mean? You are configuring the APB2 prescaler with 1:2. Right? That means whatever AHB clock you are giving here, that will be available at the output. Prescaler operation will not be done. Right? So PPRE2 is used for configuring APB prescaler. Since I am configuring it as 0, 0, 0, whatever AHB is given, that same clock will be given at the output. That means prescaler is not there. Similarly, next bit, bit number 10, 11 and 12, that is used for configuring low speed APB prescaler. That is APB1 prescaler. So this is applicable for my UART2. UART2 is connected to APB1. So based on the configuration you are giving in bit number 10 to 11, you are configuring the prescaler for APB1. Based on that, the baud rate calculation will be different. But by default, these three bits are also zeros. That means whatever AHB clock you are giving as input to the APB1, the same clock will be available at the output of APB1. So both APB2 and APB1 is receiving clock from the AHB. So here, since both APB1 and APB2 is configured with 0, 0, 0, what does it mean? Whatever AHB clock you are giving to both APB1 and APB2 input, the same clock will be available at the output of APB1 and APB2. Then the next bits 4 to 7, this is used for configuring AHB prescaler. In the block diagram we have seen that AHB itself is having a prescaler. That prescaler is configured by bit number 4 to 7. So since the reset value is 0, by default this AHB prescaler is also zeros. So 0, 0, 0 means system clock is not divided. Why it is written system clock is not divided? Because as an input to the AHB, system clock is connected. The system clock is connected as an input to the AHB. So if the AHB prescaler is not set, or if the prescaler ratio is 1:1, what does it mean? Whatever system clock you are giving to the AHB input, that same clock will be connected at the output. So by default, AHB prescaler is set to 1:1. That means whatever system clock you are giving here will be coming at the output of AHB, and APB1 prescaler is also configured as 1:1. That means prescaler is not there. So whatever AHB clock you are giving here, that will be coming at the output. So by default, both this AHB and APB1 prescalers is configured as 1:1. That means these two prescalers are not there. So the system clock, what you are giving as input here, will be given directly to UART according to my configuration. These two are configured as 1:1. That means prescaler is not there. Next register is known as APB1 Enable register, because we have seen that UART is connected to APB1 bus. So whatever peripheral you are configuring, that peripheral clock should be enabled. By default, almost all the peripherals will not be getting any clock, right? So whenever you need to enable a peripheral, you need to enable the clock to that peripheral, right? So there are two registers, APB1 enable and APB2 enable. So which register you need to select based on to which bus the peripheral is connected to. So USART2 is connected to APB1, we have seen in the block diagram. So we need to configure APB1 enable register. And APB1 enable register, which bit you need to configure? 17th bit. So APB1 enable or equal to 0x2000. That means 17th bit of APB1 enable register we are setting. That means we are enabling clock to USART2. Then we can see which are the actual pins to which the UART transmit and receive functionalities associated with this. So from this table you can see that UART2 TX is connected to PA2, UART2 RX is connected to PA3. And the alternate functionality that should be selected is alternate functionality 7. This we will see later. So now you need to understand that UART2 TX is nothing but PA2, UART2 RX is nothing but PA3. So you need to configure PA2 and PA3 as UART2 transmit and receive pin. If you are using UART1, you need to configure PA9 and PA10 like that. So now you need to configure PA2 and PA3 as UART TX and UART RX pin. So how will you configure the functionality? By default, PA2 and PA3 will be configured as GPIO pins, which is in input direction. We need to configure the functionality of PA2 and PA3 as UART pins. How will you configure the functionality of a pin? By using mode selection register. Since you are configuring PA2 and PA3, you need to configure the mode for GPIO A. So I am taking GPIO A mode selection register. So in the mode selection register, set of 2 bits are used for configuring the functionality of each pin. So here I need to configure functionality of PA2 and PA3. So which bits you need to take or you need to configure? In order to configure functionality of PA2, we need to configure bit number 4 and 5. Right? Similarly, if you want to configure the functionality of PA3, you need to configure bit number 6 and 7 of GPIO-A mode selection register. And what value you need to write? If you are writing 0, 0 in these 2 bits, that particular pin will be configured as GPIO input. If we are configuring 0, 1 in any of these bits, it will be configured as GPIO output. So by default, it will be 0, 0. Similarly, if we are writing 1, 0 to a bit, a set of bit, that corresponding pin will be configured as with alternate function. There are so many alternate functions, we will see later. So in the previous slide, we have seen that in order to configure the PA2 and PA3 as UART, you need to configure the alternate function. So in this step, what you are going to do? You are going to configure PA2 and PA3 in alternate function mode. So how will you configure PA2 in alternate function mode? Bit number 4 and 5 should be written with 1, 0. That is, 5th bit should be 1, 4th bit should be 0. Right? So that is what you are setting here. Mode selection and equal to tilde of 30 means these 2 bits are 1s, that is bit number 4 and 5. So in this step, you are clearing bit number 4 and 5. Why? Because it is and equal to and tilde is there. So tilde 1, 1, wherever 1 is there, that bit will be cleared. We have already seen. So you have cleared bit number 5 and 4. Then in the next step, you are setting bit number 5. That is why OR equal to 0x20. OR equal to 0x20 means the 0, 0, 1, 0, 0, 0, 0, 0. That means 5th bit you are setting. So 5th bit is set, 4th bit is cleared. That means you are configuring PA2 with alternate function mode. PA2 is configured as alternate function mode. Why? Because in the next step you are going to configure which alternate function you need to configure. So now you are only configuring that PA2 is in alternate function mode. Which alternate function we will configure in the next step. So these 2 steps need to be written if we are performing serial transmission, because we need to configure TX as alternate function. Similarly, I need to configure RX also as alternate function if you want to perform serial reception. So at the time of serial reception, which bit you need to configure? You need to configure PA3. Which pin? PA3. Why? Because PA3 is the RX pin of UART2. So PA3 also should be configured with alternate function. How will I do that? Bit number 6 and 7 also should be written with 1, 0. That means 7 should be set, 6 should be clear. So when you are writing 1, 0 to 7 and 6, you are configuring PA3 in alternate function mode. So in the first step, you are clearing bit number 7 and 6. That is why AND equal to tilde C0 is there. In the next step, OR equal to 80 is there. That is 1, 0, 0, 0, 0, 0, 0. That means 7th bit you are setting. 7th bit is set, 6th bit is clear. That means PA3 also is configured with the alternate function mode. So this is a diagram showing the alternate functionality which is provided for each pin. So each pin of all the ports can have maximum total 15 alternate functionalities, right? So there are two registers used for configuring the alternate functionalities. It is known as AFRL and AFRH. That is alternate functionality register low and alternate functionality register high. So alternate functionality register low, that is a 32-bit register. This register is used for configuring any of this functionality to pin number 0 to 7 of any of the ports. So pin number 0 to 7 alternate functionality can be configured by AFRL. And AFRH is used for configuring the alternate functionalities for pin number 8 to 15 of any of the port. Right. That is why it is given as GPIOX, AFRH and GPIOX, AFRL. So for all the ports, this is applicable. So if you want to configure alternate functionality for pin number 0 to 7, you need to use AFRL. And if you want to configure any one of the alternate functionality for pin number 8 to 15, you need to configure AFRH. So you can see that total 15 are there. So if you are configuring particular pin with alternate functionality 0, that will be having the system function. If you are configuring it as AFR1, it will be that pin will be having timer 1 or timer 2 function. Similarly, you can see that if you are configuring a pin as AF7, that is alternate functionality 7, it will be having or it will be configured with the functionality of UART from 1 to 3. So in my case, I need to configure my PA2 and PA3 with alternate functionality 7. So since I am going to configure PA2 and 3, which register I need to use? AFRL, because AFRL is used for configuring the alternate functionality of pin number 0 to 7. And one more thing you need to keep in mind, if you want to configure the AFRL, if the configuration need to be accepted by the processor, the mode selection bit, that particular pin should be in alternate function mode. That means you need to write 1, 0 to that particular pin in mode selection register, mode register. Because if you are writing 1, 0 to a particular pin or 2 bits of mode selection register, then only that pin will be in configured in alternate function mode. So if a pin is configured in alternate function mode, then only I can configure the particular alternate function in any of these two registers. Otherwise, even though you are configuring any of these two registers, it will be invalid if you are not configuring the mode register with 1, 0. That is why in the previous step, we have configured PA2 and PA3 in alternate function mode by writing 1, 0 to both the pins. Right. So in the next step, we can configure the alternate functionality for those two. So how can you find what are the alternate functionalities associated with each pin? Let us take this. Let us go through this table. So this is a table showing the alternate functions of port A, that is PA0 to PA15. So you can see that PA2 and PA3 alternate function 7 is nothing but UART to TX and UART to RX. So PA2, if you are configuring alternate function 7, it will be configured with the functionality of UART to TX. Similarly, if you are configuring alternate functionality 7 for PA3, you are configuring the functionality of PA3 as UART to RX. So I need to configure alternate function 7 for both the pins. So which register I need to use? Alternate functionality select register low. So this is that register. This is AFRL register, alternate functionality register low. Why? Because we are going to configure PA2 and PA3. Right? So AFRL is used for configuring functionalities alternate function of pins from 0 to 7. So here you can see set of 4 bits are used for configuring the alternate functionality for each pin. Why 4 bits? Because 16 functionalities can be selected. So A0 to A15, total 16 functionality. So 4 bits are dedicated for configuring the alternate functionality of each pin. So bit number 0 to 3 is used for configuring the alternate functionality of PA0 or pin number 0. That is why AFRL 0 it is written. Right? Then AFRL 1, that means bit number 4 to 7 it is used for configuring the alternate functionality of PA1. But in my case I need to configure the alternate functionality of PA2 and PA3. So which bits I need to take for configuring alternate functionality of PA2? I need to configure bit number 8 to 11. These 4 bits. Right? So how will I configure this? And what value I need to write here? I need to write a value 0, 1, 1, 1. So if I am writing 0, 1, 1, 1 in a particular 4 bits, that corresponding pin. So in my case, bit number 8 to 11, I am writing 0, 1, 1, 1. That means PA2 will be configured with the alternate functionality 7. So in the first step, I am writing and equal to tilde of 0x 0f 0 0. That means tilde of 1 1 1 1, then 8 zeros. That means we are clearing bit number 8 to 11. 8, 9, 10 and 11 initially we are clearing. Then you are writing or equal to 7 0 0. That means 7 means what? 0 1 1 1. That means bit number 10, 9 and 8 will be set and bit number 11 will be clear. Right. So by writing 0 1 1 1 to bit number 11 to 8 you are configuring PA2 with alternate functionality 7. What is alternate functionality 7? UR2TX. And here why it is written AFR bracket 0? Why? Because we are configuring AFRL. This AFRL is represented by AFR in bracket 0. Right? That is 0th register of AFR. AFRH will be represented by AFR1. So since I am configuring pin number functionality of PA2 and PA3, I need to configure AFRL that is represented by AFR0. If you are configuring pins from 8 to 15, I need to select AFR1. So here by writing AFR0 equal to 0 1 1 1 in these bits we are configuring PA2 as A7. Similarly, if you want to perform serial reception, PA3 also should be configured as AF7. PA3, what is alternate functionality 7? UART to RX. So what you should do? You need to write the same value 0 1 1 1 in bit number 15 to 12. Bit number 15 to 12 you need to write 0 1 1 1. So in this step you are clearing bit number 15 to 12 by writing and equal to tilde F000. We are clearing 15 to 11, 15 to 12. Then the next step you are writing 700 or equal to. That means you are writing 0 1 1 1 to these 4 bits. That means you are configuring PA3 as AF7. So if you want to perform both reception and transmission, these 4 steps need to be done. If you are performing only transmission, you need to write only these 2. If you are performing only reception, you need to write only these 2. So you need to again keep in mind, if you want to write some value into AFRL, in the previous step, mode selection register should be written with the 10. That means corresponding pin should be configured with the alternate function mode. Then only this will be coming into effect. Then we need to select proper oversampling method. What is the function of oversampling method? Or what is the use of oversampling? The receiver implements different user configurable oversampling techniques except in synchronous mode for data recovery. That means for data reception, oversampling method is used. Why? For discriminating between valid incoming data or noise. So at the time of serial reception, we are performing the oversampling. Why? In order to check whether the received bit is a correct valid data or a noise. So you can have oversampling by 16 or oversampling by 8. So what do you mean by oversampling? You are actually dividing the board clock by 8 or 16. That means whenever you are getting or receiving a bit, each bit will be can be sampled by 16 or by 8. So in one clock you will be receiving one bit, and each bit can be sampled 16 times or 8 times. That means you are performing the sampling 16 or 8 times than the baud rate clock, right? So if you want to select the oversampling by 8, there is a particular bit known as over 8 bits in the configuration register 1 that should be set. If you are writing over 8 bit as 1 in configuration register 1, we are configuring the oversampling as oversampling by 8. That means peak clock will be divided by 8, right? So you can achieve higher discrimination by dividing the peak clock or peripheral clock frequency by 8. Board clock will be divided by 8. Similarly, if you want to configure oversampling by 16, what you should do? Oversampling 8 bit should be cleared. So if oversampling 8 bit is cleared in CR1 register, that means you are configuring oversampling by 8. So if you are oversampling by 16, that means more speed will be limited, more speed will be there for the recovery, right? And it will be more accurate if we are having more sampling or oversampling. So here the peak clock will be divided by 16. Then how are you evaluating a received data? You have configured the oversampling rate. After performing the oversampling, how will you evaluate the data? So there is a particular bit known as 1 bit in control register 3. This register 1 bit, this bit is used for selecting the method to evaluate the logic. So there are two options possible. One is known as majority voting of 3 samples in the center of received bit. I told each bit will be sampled by 16 or sampled by 8, and the sender 3 bits or 3 samples, and not the sender 3 bits, 3 samples of the single bit, sender 3 samples of the single bit can be used in majority voting method. That is the first method of evaluation of received data. So what do you mean by majority voting of the sender 3 samples? When the 3 samples which are received, which are sampled, if all the 3 samples are equal, then it is identified as a valid data. If any one of the 3 samples which is sampled at the sender is not the same, then it identifies that it is a noise, it is not a received, it is not a valid data. So how will you identify that? Noise flag in status register will be set, right? So if you are writing 1 bit in the control register as 0, that means you are configuring the majority voting of the sender 3 samples. And if all the 3 samples sampled at the sender are same, that means it is a valid data. If any one of the sample is different, then it will identify that it is not a valid data, and it will be represented by setting noise flag bit in status register as 1. Then the next option for evaluation of received data is a single sample in the center of the received bit is taken. So here 3 samples in the center of the received bit will be taken, or you can configure in this case only 1 sample from the center of bit is taken. So if that 1 bit is correct, it is taken as a valid data or an invalid data. So how will you configure a single sample configuration? So by configuring one bit as 1, you can select the evaluation of received data as a single sample method. So single sample method means in the center of the received byte, only one bit will be taken for evaluating the data. How can you configure it? By configuring one bit as 1. For configuring the majority vote of 3 samples taken from the sender, you need to configure one bit as 0. Where is this one bit available? In the control register 3. Then when the noise is detected in a frame, what will happen? The noise flag bit will be set at the rising edge of RxNE. This RxNE we will see later. So noise flag bit will be set once the reception is over, and the invalid data will be transferred from shift register to the data register. So noise flag will be set, invalid data will be sent from shift register to data register, and no interrupt will be generated in the case of single byte communication. So these three functions will be done when a noise is detected. So how can you identify whether it is a noise or not? By using any of three methods. You can either take 3 samples from the sender by configuring one bit as 0, or you can take single sample from the sender by configuring one bit as 1. So this is a timing diagram showing the oversampling by 16 and oversampling by 8. So this is one bit, one bit, whenever it is received, it is sampled 16 times if we are configuring it as oversampling by 16. Similarly here, the same one bit will be sampled only 8 times if we are configuring the oversampling as 8. And in both the cases, we are using the majority voting method. What does it mean? In the center of this one bit, 3 samples will be taken, and these 3 samples are showing as same bit. Say let us take you are receiving a 0. So all the 3 samples should show it as 0, 0, 0. Then only it is taken as a valid data. If any one of the sample is non-zero, then noise flag will be set. Right? So this is where majority voting is done. But in the case of single sample method, what does it mean? In the center of the 16 samples or 8 samples, only one sample will be checked. If it is 1, it is 1, otherwise it is 0. Right. So generally we will be using the 3 sampling method, where 3 samples are taken, and if all the 3 samples are same, it is taken as a valid data. So here when you are performing oversampling by 8, each sample will be divided 16 times. That is why we have seen that it is peak clock by 16. But in oversampling by 8, each sample will be divided by 8. So it is peak clock by frequency of peak clock by 8. So by configuring the control register, we can have certain configuration for the UART1. So these are the bits present in the control register 1. So here in the slide we can see that we are configuring TE and RE bit. What do you mean by TE? It is a transmitter enable bit. RE is receiver enable bit. So if you are performing transmission, you need to enable TE bit by writing 1 to this bit. So if you are writing 1, transmitter will be enabled. If you are writing 1 in second bit, the receiver will be enabled, and it will start searching for start bit. So if you are using transmitter, you will be writing UART2 control register equal to 0008. That means the third bit you are setting it as 1. That means transmitter is enabled. If you are writing 004, that means the second bit you are making it as 1. That is the receiver is enabled. Then in the same control register, 12th bit we are concentrating. This 12th bit is used for configuring the word length. Right? Word length. So if we are writing the 12th bit as 0, what does it mean? 1 start bit will be there, 8 data bits will be there, and n stop bits will be there. Number of stop bits will be configuring in the next step. We will see later. Right? So we are writing bit number 12 as 0. That means we need to configure 1 start bit, 8 data bits, and n stop bit. If you want to configure 9 data bits, you need to write it as 1. but for time being I am configuring only 8 data bits as my word length. So I am writing 0 in bit number 12. So UR2 CR2 equal to 0008. That means bit number 12 you are writing to 0. That means 1 start bit, 8 data bits, n stop bits. Then next bit in the same register I am going to configure is bit number 15. This is known as the over 8 bit. This is used for configuring whether you are selecting oversampling by 16 or oversampling by 8. By default 0 will be there here. Right? I am using only 0. By default also it will be 0. By default all the values will be zeros. So if we are writing 0 in oversampling 8, what does it mean? We are configuring the oversampling by 16. So here how will I set it to 0? I am writing CR1 equal to 008. Right? So by writing CR1 equal to 008, you are configuring all these things. You are configuring TE and RE. Right? If you want to configure TE, 8 will be written. RE, 4 will be written. Right? And if you are writing 8 or 4, in both the cases, the word length, that is m bit, is 0. That means 8 data bits. Then oversampling bit also will be 0. Right. So by writing 008, that means you are configuring oversampling as 16, data bits as 8, and transmission enabled. If you are writing 0004, then oversampling by 16, then m will be, data bits will be 8, and receive enable will be 1. Then the 13th bit we need to again see in the same register. So 13th bit is nothing but UART enable bit. So if it is 0, what does it mean? UART will be disabled. If it is 1, UART will be enabled. So initially when you are writing 0008, what does it mean? The 13th bit is 0. That means UART is disabled along with other configuration. Right? Even though the oversampling and data bits and transmission is configured, UART will be disabled. And once all the configuration related to the UART, that is configuration of CR1, configuration of CR2, configuration of CR3 and board registers, whatever configuration you need to do for the UART. After doing all the configuration, the last step will be setting this 13th bit to 1. Right? So in CR1 I am writing or equal to 20. That means 13th bit will be 1. So this statement will be written after configuring all the necessary bits required for USART transmission or reception. So initially I am making this bit as 0. That is why I am writing CR1 equal to 008. That means UART is disabled. And once all the configuration of UART is over, you need to set this 13th bit to 1. Right? So the last step of UART configuration will be CR1 or equal to 200. That means you are enabling the UART. So this should be given as the last step. You need to keep in mind. So in this step, you are configuring the UART control register 2, that is CR2. So here the main configuration that you are doing in control 2 is you are configuring the stop bit. So bit number 13 and 12 is used for configuring the stop bit. Right? So if you are writing 00, that means one stop bit will be configured. If you are writing 01, it will be 0.5 stop bit, 10, 2 stop bit, 11, 1.5 stop bit. For time being, I am configuring it as 1 stop bit. So what value should I write? I need to write it as 00. So by default, again it will be 0. Right? So by default 00 is written here. That means 1 stop bit will be configured. So what will be the UART CR2 value? 0x00. That means here we are concentrating only on the stop bit. 00 means 1 stop bit. Others are not used for time being. Then the next register you need to configure is UART CR3 register, control register 3. So in this control register 3, as you have seen before, we need to configure this 1 bit. 1 bit is used for configuring whether you are using 3 samples at the sender for the evaluation of bit or single sample at the center for evaluation of bit. By default, this one bit will be set to 0. That means 3 sampling method will be used for the configuration. By default, this is set to 0. So 3 samples will be sampled at the center, and if any one of the bit is not same, then noise flag will be set. Otherwise, noise flag will be reset. Right. So here I am setting 1 bit to 0. That means 3 sampling method is used. That is why 0 is set in bit number 11. And the other bits are used for flow control. This flow control also I am not using. That is why all the other bits are 0. So by default, flow control is not there. Flow control means acknowledge bits are not used in our serial transmission. We are not using any acknowledgement bits. So by writing CR3 equal to 000 means 3 sampling you are configuring and no flow control you are using. So we have configured almost all the registers. Few more registers you need to configure. One of the important register you need to configure is the baud rate. So in order to configure a particular baud rate, you need to write a value in a register known as baud rate register BRR. But how will you calculate the value that is to be written into BRR in order to configure a particular baud rate? That is what you are going to see here. So for time being, you are going to perform the baud rate calculation for oversampling by 16. That means over 8 bit will be 0. So if we are performing oversampling by 16, what will be the baud rate equation? Baud rate equal to PCLK by 8 into 2 minus over 8 bit into USART div. This is the value that is to be loaded into baud rate register in order to configure a particular baud rate. Right. So if you are moving this value to BRR, particular baud rate will be generated. So how will you calculate this baud rate value? You can rearrange this equation. So since here we are using oversampling by 8, oversampling by 16, this oversampling bit will be considered as 0 here. Since oversampling is by 16, oversampling bit will be 0. So I am taking 0. So you can have the equation as PCLK by 8 into 2 into UR div. So by rearranging this, UR div equal to P clock by 16 into baud rate. So by using this equation, you can calculate the value of UR div. So for an example, we are assuming that P clock is 16 MHz. By default, P clock or APB clock, P clock means it is peripheral clock. It is nothing but the APB clock. So by default, APB clock is 16 because none of the prescalers are configured. We have seen in the previous slide. Then I am going to configure, I need to have a baud rate 9600. Oversampling, I am configuring it as 16. That means over 8 bit is 0. So provided these assumptions, what value should be getting in UART div? For what value should be moved to BRR? How will you calculate this? UART div equal to, what is peak clock? 16 MHz by 16 into baud rate. That is the equation, peak clock by 16 into baud rate. So when you are substituting 16 MHz, then 16 and baud rate as 9600, you will get UART div as 104.166. So 104 is the Mandisa part. If you are writing in hexadecimal, it will be 0x68. 0.16 is the fraction part. So you need to convert this fraction also into a particular number, a whole number. So I am doing 0166 into 16. Why this into 16? Because you are performing oversampling by 16. So since oversampling by 16, what you will do with the fraction? Fraction you need to multiply by 16. So you will be getting 2.656. You are rounding off to 3. So here, if you want to configure baud rate as 9600, provided PCLK is 16 and oversampling is 16, your UART div value will be 104.16. That means the divisor Mandisa will be 0x68 and the fraction will be 0x03. So these two values we are configuring in the baud rate generator register, that is BRR, in order to generate 9600 baud rate. So similarly, if you are performing the same calculation with oversampling as 8, what modification will be there? Instead of in 2 minus oversampling 8, here oversampling will be 1. So it will be 2 minus 1. So instead of 16 into UART div, here it will be peak clock by 8 into UART, because it is 2 minus 1. Oversampling is 1, showing that oversampling 8 bit is 1, showing that we are performing oversampling by 8. So same assumption we are taking, peak clock equal to 16 megahertz, baud rate is 9600, but oversampling is done by 8. So what will be the value of UART div? 16 megahertz by 8 into 9600. So you will get it as 280.33. So the Mandisa will be 280. So the hexadecimal value is 0x118. Fraction will be 0.33, and here since oversampling is by 8, you need to multiply by 8. So 0.33 into 8. So you will get it as 2.64. You are rounding off to 3. So if you are writing 0x11 and 0x03 in the corresponding Mandisa and fraction of BRR register, you are configuring the baud rate as 9600. Now we will see how can you write into the baud rate generator register. So this is known as a baud rate generator register, BRR, USART x BRR. So if you are configuring oversampling by 16 or oversampling by 8, you need to write the fraction part in bit number 0 to 3 and Mandisa part from bit number 4 to 16. So Mandisa, you can have maximum only these many bits. Fraction can have only maximum 4 bits. Above this value, you will not be able to configure. So bit number 0 to 11, that is 12 bits, starting from actual bit position 4 to 12. So only 12 bits Mandisa is possible and 4 bits fraction is possible. So in the previous example, if PCLK is 16, baud rate if you want to generate 9600 and oversampling is by 16, what was the value for Mandisa and fraction? We have calculated the Mandisa as 0x68 and fraction as 0x03. So what will happen? The 0x68 should be written here and 0x3 should be written here. That means if you are moving 0x0683 to BRR, that means Mandisa you are configuring as 68 and fraction you are configuring as 3. That means by writing 0x0683 to BRR, provided oversampling is 16 and peak clock is 16, we will be generating 9600 baud rate clock. Similarly, for oversampling 8, the same register you are using, same fraction and Mandisa part you need to configure, but only the value is changing. PCLK is 16, baud rate I need to generate is 9600, but since my oversampling is by 8, my Mandisa value will be 0x118, fraction will be 8. So this 118 should be written to Mandisa part, 3 should be written to fraction part. So if I am writing 0x1183 to BRR register, that means you are configuring baud rate as 9600 provided PCLK is 16 MHz and oversampling is by 8. So this is how you are configuring the baud rate generator register. Right. So this is a table showing the corresponding baud rates and the value that need to be written into BRR. Right. So if you want to configure 9600 baud rate, provided oversampling is 16 and PCLK is 16, BRR should be loaded with 0683. This calculation we have seen in the previous slide. If I want to configure 115200 bits per second, the unit is bits per second. then what value you should send it to BRR? 0x0008b. So similarly for oversampling by 8 and PCLK by 16, these are the values. So if the oversampling by 8 and 9600 baud rate you need to generate, you need to move 0x1183 if PCLK is 16. So some of the values they are provided in the table, so no need of calculating it. So this register is known as a status register. This status register is used to identify or represent the status of transmission or reception. When the transmission is over, TXE bit, that is transmit data register empty bit, will be set. Right? Transmit data register empty, that is known as TXE. If it is set, what does it mean? The data has been transferred to the shift register from the transmit data register. We are sending the data to transmit data register. Once this bit is set, what does it mean? Transmit data register has completely sent this data to the shift register. That means new data can be sent to the TDR. So if the transmit data register is empty, that means new data can be sent to the TDR. So before performing any of the serial transmission or before sending the data to the data register, UART data register, because data register is used for sending the data for transmission. So whatever data I need to transmit, I need to send it to data register. So before sending a data to the data register, I need to check whether transmitter is ready to receive the new data. How will I check that? I need to check whether TXE is 1. If TXE is 0, that means some transmission, previous data transmission is going on. So I need to wait until TXE is 1. So how will I do that? I am writing while not of UR to SR and 0080. Why I am ANDing the status register with 80? Because I need to split the 7th bit or extract the 7th bit and mask all the other bits to 0. So when I am ANDing with 0080 means I am only extracting this 7th bit and I am masking all the other bits as 0. So if this value is equal to 0, that means this while condition will be true. If this bit is 0, that means all the other bits you have already masked to 0. So the value of this will be 0. So this exclamation shows that UART SR and 0x80 equal to 0. So the equal to 0 is represented by the exclamation. So if this condition is true, the program will wait in this statement itself, in while condition itself, because it don't have any statement. So until UART 0 is 0, we will be waiting in this statement, right? And when TXE bit is 1, this statement will be skipped. That means this condition will be false, and whatever data you need to send, here the CH is represented by the data. Here the CH is represented by the received character. That received character will be ANDed with 0xFF in order to avoid the bits more than 8 bits, because only 8 bits you can transmit through UART. So this value you are sending to data register. So before sending the character to a data register, you need to wait until TXE is 1. If TXE is 0, you need to wait there. If TXE is 1, you can send the data to data register. Next bit in the status register is known as the RXNE bit, that is read data register not empty. TXE means transmit data register empty. That means if the data register is empty, then only you can send the new data for the transmitter to transmit. But here RXNE stands for read data register not empty. Why? Because if the data register which is receiving the data, which receives the character, is not empty, that means the reception is over. So how will you identify the reception is over? The read data register or the UART data register should not be empty. If it is full with the data, if the received data register is full with the data, that means the reception is over. So how will you identify the reception is over? you need to wait until RxNE bit, that is received data register, is not empty, or you need to wait until RxNE bit is 1, right? So if it is 1, what does it mean? Received data is ready to be read by the user. That means the reception is over. So previously what you have done, you have splitted the TXE bit and you are ANDing that with SR. SR and 0080 means you are splitting TXE and all the other bits you are masking. Similarly here, you are ANDing the status register with the 20. That means you are extracting the 5th bit alone, all the other bits we are masking. So UART2 status register and 0020 means you are extracting the 5th bit alone. And as you have done in the previous step, you are checking whether the ANDed value is equal to 0. If it is equal to 0, we need to wait here, because if it is equal to 0 means RxNE bit is 0, that means some reception is going on. We need to wait until RxNE is 1. If RxNE is 1, that means the reception is over, so that the meaningful data will be available in UART data register. Right, from the data register you can read it to a data variable. Here data shows that it is a variable used for storing my received data. So you need to read from the data register to a data variable only if RxNE bit is set. So this is a data register which is used for both reception as well as transmission. There are only 8 bits because we can perform only 8-bit data transmission or reception using UART. So this is how you are performing the configuration of UART peripheral. So now we are going to see program for continuous transmission of a character A from the STM32 microcontroller to PC through UART2. So this is the main program. In the main program, first of all you are calling a function known as UART2 init. So this is a UART2 initialization program. So first of all, APB1 ENR or equal to 1. That means you are enabling for clock for GPIO A, because PA2 and PA3 is used for UART. Then APB1 ENR equal to, you are writing or equal to 2000. That means you are enabling clock for UART2. So for enabling clock for all the peripherals, you are using enable registers. Since GPIO is A is connected to AHB1, so AHB1 enable register you are configuring. UART2 is connected to APB1, so APB1 enable register you are configuring. As the next step, you need to configure the functionality of PA2 as UART2. So for that, you need to configure the mode selection registers. So by using these two statements, you are configuring PA2 with the alternate function mode. So whenever you are writing 10 to a particular bit, particular 2 bits of mode selection register, that corresponding pin will be configured with the alternate function mode. If you are writing 00, that pin will be input. When you are writing 01, it will be output. And 10, if you are writing to 2 bits, that corresponding pin will be configured with alternate function. So here PA2 I am configuring with the alternate function by using these two statements. After that, you are configuring what alternate function you need to configure. In these two statements, you are defining what alternate function you need to configure for PA2. So here for PA2, I need to configure alternate function 7. That is nothing but UART2 TX. So PA2 you are configuring with the alternate function 7. So in the alternate function register, 4 bits are used for configuring the alternate function for each bit, for each pin. So when you are writing 0x or equal to 0x0700 means you are configuring the 4-bit value as 0111. That means the corresponding pin will be configured with the alternate function 7. So when you are writing 700, that means PA2 will be configured with the alternate function 7. We have already seen in the presentation. You can go through it if you are having any doubt. And why you are writing AFR 0 because alternate function register low is there, alternate function register high is there. So alternate function register low is used for configuring the alternate function to pins 0 to 7. Here, since I need to configure the alternate function for PA2, I am using alternate function low register. So that low register is represented by 0. If you are configuring alternate function high, this 0 should be replaced with 1. Then as the next step, you are configuring the baud rate as 9600 provided PCLK is 16, right, and the oversampling is 16. So in this step you are configuring the baud rate with 0x0683. This calculation also we have seen. If you are having any doubt, you can go through that. So here you are configuring the baud rate as 9600 at PCLK 16 MHz. Then you are to CR1 control register 1, you are writing 008. That means you are enabling TX. That is TX bit, you are enabling the transmitter. TE bit you are making it as 1, and the data length you are configuring it as 8 bit. So CR1 equal to 008 means you are enabling the transmission and data length is 8 bit. Then CR2 you are writing the default value, that is 000. That means you are configuring one stop bit. In CR2 the main configuration is configuring the stop bit. Then CR3 also you are writing 000. That means no flow control will be given here, and one bit will be set as 0. One bit is used for configuring whether majority voting with the 3 samples taken from middle or 1 sample should be taken from the middle. By default 1 bit is 0, so 3 samples will be taken from the middle, and flow control is non-flow control. Then after configuring all the UART configurations, as the last step you need to make CR1 equal to 2000. That means the 200 means you are enabling the UART. Right, UE bit is there in CR1. So if you are making UE bit as 1, you are enabling the UART. But you need to take care that this UE bit should be enabled as 1 once all the other configuration is over. Otherwise, when you are making UART UE as 1, with whatever configuration you have written onto the UART registers, it will start working. You need to take care that once all the configuration is done, then only you should make UE bit as 1. So this is a UART initialization function. Then in while 1, this is a program for continuous transmission of a character. So A should be transmitted continuously. For that you are using a function known as UART2write. This is used for sending a character through UART TX pin. So here you are using UART2. So how can you do that? Whatever value you are giving in this function, that character will be sent to data register. If you are sending a data register, that data will be sent out through the TX pin. And I have already told that before sending a data to the data register, you need to check whether TXE bit is 1. TXE stands for transmit data empty. Right. If transmit data is empty means the data present in that there is no data present in the transmit register, so that new data can be sent to that register. Right. So before sending a character, you need to wait until TXE is 1. If TXE is 0, you will wait in this while loop itself, because the condition will be true. And why you are using AND equal to 0x80? You are splitting the TXE bit alone and you are masking all the other bits. You are extracting TXE bit and masking all the other bits. So this value, if it is equal to 0, we will be waiting in the while loop itself. If it is 1, this condition will be false. So the control will come to this statement and the character will be ANDed with 0xFF in order to ensure that only 8-bit character is sent, and that data is sent to the data register. So when you are sending a character to a data register, it will be transmitted out, and you are giving a delay of 10 millisecond. It is generated using a delay millisecond function. So this is a program for transmission of a character through UART2. So the next program is for reception and transmission of a character. So first of all, you need to receive a character that is sent from the laptop. So if you want to send a character from the laptop, first you need to have a serial terminal software. You need to open that software, and keeping it open, if you are typing some characters in the keyboard of the laptop or desktop, the ASCII value of that character will be sent out through the serial port. So what does the controller do? Controller should receive the data coming from the PC through the UART2, and that character which is received, you are going to transmit it back. So this is a program for receiving a character received on UART2 from the PC and transmitting that character back to the PC so that it will be displayed on the serial terminal, and both the reception and transmission is carried out in 9600 baud rate. So only few steps are different in the case of transmission and reception. So first of all, you are initializing the UART. The initialization of the UART is almost the same, right? So what you are doing? APB1 Enable ENR register, you are making one. That means you are enabling clock to GPIO. Then APB1 ENR, you are writing 2000. That means UART2 clock you are enabling. Then in the next step, you are configuring PA3 as UART2 receive. In the previous program, for the transmission of the program, this part you have seen. So in addition to configuring PA2 as transmit, you need to configure PA3 also as receive. So how will you do that? First of all, PA3 should be configured with alternate function mode. How will you do that? These two steps. Using the mode selection register, we are configuring the functionality of PA3 as alternate function mode. Then by using these two steps, you are configuring alternate function 7 to UART2. That is, PA3 will be configured with the alternate function 7. Right? So that is why you are writing or equal to 7000 and equal to tilde of F000 means the 4 bit of alternate function register you are clearing. Then to those 4 bits you are writing 0111. So by writing 7000, you are configuring PA3 with the alternate functionality 7. So these statements are used for configuring PA3 as UART RX functionality, and this statement we have already seen. This is used for configuring PA2 as UART TX functionality. Then these statements also you have seen, right? So BRR equal to 0x683 means you are configuring 9600 baud rate at 16 MHz peak clock. Then in CR1, previously you have written 0008. What does that mean? 0008, you can see here. If you are writing 0008, that means you are enabling transmission. There is a bit known as TE bit in CR1 that you are making it as 1, transmission will be enabled. Similar to that, you need to make RE bit also in CR1 as 1. Why? Because you need to perform enable. So receive enable also should be made as 1. How will you make it 1? CR1 equal to 0004. CR1 equal to 0004. Then in addition to that, you need to enable TX also. So both the TX and RX should be enabled. So how will I do that? So first of all, you are writing 004. So RX will be enabled. Then you need to write 0008. But you need to keep in mind that if you are writing a particular value to a same register, previous register value will be overwritten. But here I don't need that. I need to enable both RX and TX. So what should I give here? I need to give here or equal to. So this is very important. So when you are writing a value to the same register which you have already written, you need to use or equal to. Otherwise, the previous value will be overwritten. So in my case, both RX and TX should be enabled. That is, TE bit and RE bit should be enabled. So I am writing CR1 equal to 0x04. After that, or equal to 0x008. That means whichever bit I am setting it as 1 here, only that bit will be modified other bits will be as it is because it is zeros. Then in CR2 you are writing 0 0, stop bit is configured as 1. CR3 you are writing 0 0, that is no flow control, and 1 bit is 0. That means the sampling will be done 3 times at the middle. Then after configuration of the whole UART, that is both the transmission and reception is configured, then only you need to make UE bit as 1. Where is UE bit present? In the same CR1. So since you are again writing to CR1, you are using or equal to. So when you are writing CR1 or equal to 200 means UART enable is 1. So UART initialization is over. Then inside while one, what I am doing? First of all, I need to read the data from the UART. Right? For that, I am using a function known as UART to read. So this is a UART to read. So it is same as UART to write. What is the difference? Only the bit which you are checking for reception is different, because for transmission, what you want to do before sending the data to data register, you need to check whether TXE flag bit is 1 in order to identify whether the transmitter is ready to receive a new character. Similarly, for the reception, in order to check whether reception is over or not, you need to wait until RXNE flag is 1. RXNE means receive data not empty. If the receive data is not empty, if the receiver register is not empty, that means the reception is complete. Right? RXNE means receive data not empty. So if the data is not empty means it is having a data. So if it is having the data, that means the reception is over. So same as you have wait until TXE1, you need to wait until RXEE1. So previously you were extracted by using a value 0080 for extracting TXE. Here instead of 80, you need to end with 0020 in order to extract RXNE bit. Right? So you are ANDing SR with 0x20, you are extracting RXNE bit, and if that bit, if the value of this is equal to 0, you will wait here. If it is 1, what does it mean? Reception is over. So the data present in UART data register will be returned to a variable, because this function is of type character. Right? So here I am writing data equal to UART to read. That means whatever data it is returned from this function. What is the data? The data which is received, that will be stored onto a character variable known as data. So this data variable contains the data that is received from the PC. Then what is the next step? The same data I need to transmit it back to PC. How will you transmit the same character back to PC? Already we have seen the serial transmission function, that is UART to write. So you will be waiting until TXE is 1. If it is 1, whatever character you have received that is present in this data, that is passed on through this function, that data will be sent to data register. So that whatever character you have received from the PC will be sent back to the PC from the controller. The controller will receive the character coming through UART to, same character it will be transmitted back to the PC through UART to, so that we can see the character in the serial terminal of the UART. So this is how serial transmission and serial reception program is working.